So I'm starting with today's discussion. I think the other day we have concentrated on this slide, which actually helped us to appreciate the fact that Navier-Stokes equation is the parent equation, and all of the equations are simplifications of this parent equation. So as far as the application part is concerned, you can look at this process in which there is a supply tank and a receiving tank. Both are connected by a kind of a pipe. So you are able to see, if you want to analyze this region, हाँ जी बताइए, you could simply use the hydrostatic equation. You need not use the Navier-Stokes equation in the entire domain. So that is the utility of using approximations of Navier-Stokes equation. The best way to do it is you could have solved Navier-Stokes equation for the entire domain. Then what would be the problem? What will be the problem if you want to solve the Navier-Stokes equation for the entire domain? Anyone? Anyone? Akash?
Yes, sir.
If you want to solve the Navier-Stokes equation for the entire system, what will be the problem?
सर कुछ फ्लोज की प्रॉब्लम आ सकती है.
फ्लोज की प्रॉब्लम मतलब
लेमिनार या टर्बुलेंट में
नहीं, लेमिनार या मान लीजिए सब कुछ लेमिनार है, देन व्हाट कैन बी द प्रॉब्लम? व्हाई कैन नॉट यू सॉल्व दिस? और कैन यू सॉल्व दिस? हाँ जी, एनीवन? You could have solved this, but then computationally it is very difficult. You will have to divide the entire domain because you cannot have numerical solution for this. You cannot have analytical solution. So you will have to resort to numerical solution. But if you want to remain in the analytical domain only, then you simply approximate the regions with different approximations. So you are able to see, you could actually treat this region as a stationary fluid region which is moving with very slow velocity. Likewise, this region. In this region, you could use the full Navier-Stokes equation. In this region, you could use irrotational flow region approximation. Here, you could use boundary layer approximation. So the entire domain could be solved by actually approximating different regions with different approximations. That is the way you do it. If you don't want to do it numerically, that is through CFD. And clear? Any doubts? So now I'm coming one by one to each of them. So we have already done this Couette flow, Poiseuille flow, Darcy-Weisbach equation. So I am now coming to another kind of approximation that is called the potential flow. So please remember, in terms of potential flow, we will be essentially dealing with two-dimensional, irrotational, inviscid, incompressible region of flow. So this is meant by potential flow. What else was also equal to zero, if you remember, in case of potential flow? What else was equal to zero? This viscous term is zero, so it is inviscid. This body force term is also zero. And it is two-dimensional. So these are the assumptions for potential flow. And if I ask you with these assumptions, How will the continuity equation look like? Can you help me to write down continuity equation in case of potential flow in XY plane? How will the continuity equation look like? What should I write down? What is the generalized continuity equation? Curly rho by curly T plus curly rho U by curly X plus curly rho V by curly Y plus curly rho W by curly Z is equal to 0. This is the generalized continuity equation for any Newtonian fluid. What about two-dimensional continuity equation in XY plane? What should I say with these assumptions? What should this transform to? Ayush, what should this transform to?
सर किसको कन्वर्ट करना है
Curly
किस में
U
करना है मतलब एक्स वाई प्लेन में
XY plane में
बाय कर्ली एक्स
plus
कर्ली
curly
यू
V
बाय कर्ली
by
एक्स प्लस कर्ली वी बाय कर्ली वाई
is equal to 0. Is that clear? Any doubts? So we define a function called, you might have heard about it, stream function. This we define because this is a scalar function. So instead of two variables, we could actually define this in terms of a single variable. And that is represented by psi. Stream function psi. And it is defined as u is equal to curly psi by curly y and v is equal to minus curly psi by curly x. So the very definition of stream function has come from continuity equation. We define a scalar function such that the continuity equation is actually valid. अब इसमें आप पुट करके देखो, u को अगर आप ये पुट करेंगे और v को ये पुट करेंगे, आंसर 0 आएगा कि नहीं आएगा? What will you get? Curly square psi curly x curly y minus curly square psi curly y curly x. So these are similar if u and v are continuous functions and psi is a continuous function, then this, you know that this order is followed. That is, you don't have difference when you change the order of differentiation. That is the same thing. So the definition of stream function comes from the continuity equation, and this is called the stream function. So please remember, stream function is defined for two-dimensional flows, and it has come from continuity equation. Is that clear? Is that clear? Now I'm coming to another function that is important in potential flows, that is called the potential function. So if you remember, in potential flows, the flow should be irrotational and inviscid. So for irrotational condition, what is the mathematical condition for flow to be irrotational? What should be equal to 0 mathematically? What should be equal to 0? Aditya. What should be equal
Yes.
to 0 for irrotational flow mathematically?
vorticity
Vorticity vector should be equal to a null vector. And what is vorticity vector, if you remember? Del cross
v vector
v vector. This should be equal to a null vector. And what do you know from the definition of this thing, if you remember? if you remember this, what is this equal to? This is curl of the gradient of a scalar function. So what do you think this is equal to? Curl of gradient of a scalar function. What should be this equal to? Curl of gradient of a scalar function. Gradient क्या होता है? Gradient gives you the direction of maximum change, and curl gives you how the field is swirling around. So what do you think the value of this should be equal to? Curl of the gradient of a scalar function. This should be equal to what? Ayush.
So 0.
A null vector.
Null vector, yes, sir.
So you are correct, Rajansh. Now try to compare these two equations. Equation number 1 and equation number 2. Can you actually relate these two equations? Right hand side of both the equations are same. What does that tell you? Velocity vector can be represented as gradient of a
Vector.
scalar function.
Scalar function, yes.
So please remember, this was only possible in which case? In case of irrotational flow. And this phi is called the potential function. So the very definition of potential function has come from what? The irrotational condition. And stream function has come from what? Continuity equation. This should be clear to you. Now if V is del phi, then what do you think is U equal to? And V equal to and W equal to? From this equation. What do you think U, V, W are equal to?
For UVW, the velocities in different axes.
Different axes. In terms of phi, what should be this equal to if you utilize this formula?
Sir, del x, मतलब star. उसी का gradient उसी format
So
में.
curly
yes.
U by curly X. This is
X.
curly V by curly Y. And this is
Mhm.
curly
V.
phi by curly X, curly phi by curly Y, and curly phi by curly
Z.
Z. Is that clear?
Yes, sir.
So we have defined two functions for two-dimensional potential flow. One is stream function and other is potential function. And we know that U is equal to what? Curly psi by curly Y. V was equal to minus curly psi by curly X. And U is also equal to curly phi by curly X. And this is equal to curly phi by curly Y. So velocities U and V have been represented in terms of scalar function psi and phi. Any doubts to anyone? So we have gone from vector functions to scalar functions. That is the benefit of this. Another benefit is you can think about, you could write down U as say curly phi by curly X and V as curly phi by curly Y. So what were the original number of variables, unknown variables? 2. Now what are the number of variables? 1. So you have actually gone from vector to scalar, and as well as you have reduced the number of variables involved in the equation. So that is the utility of these functions as far as potential flows are concerned. So please keep this at the in mind that potential flows are just special cases of the Navier-Stokes equation that we have already studied. This was the Navier-Stokes equation. This is just an approximation of Navier-Stokes equation. And when we apply this approximation, we are actually able to analyze inviscid irrotational regions of flow without solving the entire Navier-Stokes equation. And to further simplify, we have utilized the concept of stream function and potential function in case of defining potential flows. That is as simple as that. Nothing more than that. And you clear hai? So we have u as curly psi by curly y, and this is equal to curly phi by curly x, and v as minus curly psi by curly x, and this is curly phi by curly y. Now, help me to write down, say, you know that any kind of flow field should satisfy this. What is this equation? Continuity equation. And we saw that stream function actually was defined using this continuity equation. So potential function also should actually satisfy this equation, because any kind of function which does not satisfy continuity equation is not valid. So when I put these values of u and v in this continuity equation, what do I get? Curly square phi curly x square plus curly square phi curly y square is equal to 0. And if you remember, what is the type of this equation? What is this equation? Type. This is two-dimensional Laplace equation, if you remember. So potential function satisfies Laplace equation in 2 dimensions. And we also know that for irrotational flow condition, if you remember, if I ask you what is vorticity vector, you know that del cross V. And if I ask you what is Ez, what will be your answer? What is Ez? Zeta Z. Zeta is a vector such that it has vorticity vectors in x, y, and z directions.
Omega.
So what should be the answer?
Omega by del z.
तो यहाँ पे क्या इसको आप लिख सकते हो मैट्रिक्स फॉर्म में? क्या लिख सकते हो? कर्ली बाय कर्ली एक्स, कर्ली बाय कर्ली वाई, कर्ली बाय कर्ली z. What else? You know that you have, I think, I, j, k. And what here? U, V,
W, omega.
W. So what will be the value of zeta z? What will be the value of zeta z?
Curly u by curly x minus curly
v by curly x.
हाँ.
Minus
Yes,
curly
sir.
u
by curly y.
Curly y.
Yes, sir.
And if you substitute the value of stream function, these two values, instead of u and v, what do you get? And you know that zeta z should be equal to what for irrotational flow?
0.
0. So when you substitute the value of u and v in terms of the stream function value, that is u is equal to curly psi by curly y, what do you get? And v is equal to minus curly psi by curly x, what do you get?
Curly square psi by curly y square.
So you get similar kind of equation.
Laplace जैसी.
So this is also satisfying the Laplace equation.
Yes, sir.
So please remember the special properties of these for two-dimensional planar inviscid irrotational incompressible flow. You have defined two functions. One was your stream function, one other was your potential function. This is called the stream function, and this is called the potential function. How did you define stream function? Through continuity equation. How did you define potential function? Through irrotational condition. And you know that u is equal to curly psi by curly y is equal to curly phi by curly x, and v is equal to minus curly psi by curly x is equal to curly phi by curly y. And also they satisfy the Laplace equation. This should be clear in mind. Is this clear to everyone? So in potential flows, we have defined two concepts, stream function and potential function. Both of them are scalar functions. Both of them satisfy their own Laplace equations. And both of them can actually define the velocity components u and v. Is that clear? And the utility of this is, it will become clear in a moment. The utility here is, you know that for this is a second order homogeneous differential equation. This is also second order homogeneous differential equation. So if I ask you, so this is an equation, and if I ask, say that phi 1 is the solution, phi 1 and phi 2 are the solution of this equation, then do you think phi 1 plus phi 2 is also the solution? This is second
No,
order
sir.
differential equation, homogeneous. If phi 1 and phi 2 are the solutions of these two, of this equation, do you think the sum of these also is also solution of this equation?
No, sir.
Try to think about it. If
The
phi 1 is
constant.
solution, what does it tell you? Curly square phi 1 plus curly x square plus curly square phi 1 curly y square is equal to 0. Likewise, curly square phi 2 plus upon curly x square plus curly square phi 2 upon curly y square is equal to 0. If phi 1 and phi 2 are solutions, then these two should hold true. Is this clear?
Yes, sir.
So now if I substitute phi is equal to phi 1 plus phi 2, what will happen? What will happen? Curly square phi 1 plus phi 2 upon curly x square plus curly square phi 1 plus phi 2 curly y square. Now, will this satisfy the Laplace equation? That is, will it this be equal to 0 or not?
Yes, sir.
This will also be equal to 0.
Yes, sir.
What about this? A phi 1 plus B phi 2.
Yes, sir. ये भी होगा.
ये भी होगा. So any linear combination is also a solution.
Yes, sir.
So that concept has been actually utilized to simplify fluid flow problems. Now I'm giving you an example here. So it means you can actually combine or superpose two potential flows or any combination of them, or say this is one solution, this is another solution, this is another solution. So you know that this is also again the solution. This is also a solution. So any linear combination of the solution themselves is also a solution. Is that clear?
Yes, sir.
So what does that tell you? Now please be careful in this. So if this is a plate and fluid is flowing past this plate, say plate is like this. This is a solid plate and fluid is flowing past this plate. So there will be a boundary layer. And above this region will be inviscid. This region will also be irrotational. So you can actually approximate this as a potential flow. Is that clear? Can you utilize this as potential flow or not? Potential flow is incompressible, inviscid, irrotational. And you know that a region of flow can be rotational only when there are viscous forces. I will come to these. Baroclinic pressure condition or non-conservative body forces. These are the three conditions in which the fluid region can be rotational. If these are not present, then the fluid region is irrotational. ये clear है सबको कि there is some doubt in this? Rajanj.
क्लियर है सर, क्लियर है, ये इतना तो सही है.
Okay. So what does that tell you? This is uniform flow. When I say uniform flow, it means I am talking about a flow which is outside the boundary layer. That is this region. So this is a rotational region. And say stream function is phi for this. Say phi uniform. I have another irrotational region of flow that is called, say, a source. So what do you mean by source? This is source. Source means, say, if you have seen springs, water is coming out of the spring.
Yes sir.
So I think in first or second class, we did something called divergence of a vector field. This tells us how much fluid is diverging from a point. And if divergence is what? Non-zero, what do you know from your basics? What will be this equal to, if you remember? Can you have curl of a divergence? Curl of divergence.
कर्ल ऑफ डाइवर्जेंस तो सर
Vorticity.
इम्प्रैक्टिकल सी चीज है ये
So
सर.
it will be a null vector. You cannot
Yes, sir.
have swirling around if something is diverging from a point.
Yes sir, right.
So it means this is also irrotational region of flow. So
Okay.
source is also irrotational. Uniform flow, which we have defined here, is also irrotational. So if this was a phi source, then this actually can result in another flow that is having phi resultant is equal to what? Phi uniform plus phi source. And this is called the principle of superposition or combining elementary irrotational flows. This is called combining elementary irrotational flows. Likewise, think about another kind of elementary flow. All of you have seen wash basin.
Yes sir.
So try to think when you brush your teeth and say, this is the drain, and say something is there, that is water has got filled here and it is stagnant here. You quickly remove this. What will happen? What kind of motion do you see?
Parabolic.
What kind of motion do you see?
Sir, round.
Spiral, sir.
Spiral.
Spiral,
Spiral.
helical path type.
So
Yes sir.
if something is there, so it will keep on moving towards this drain.
Yes sir.
Is that clear?
Yes sir.
Now let me know what kind of things are here. Is something converging to the drain?
Yes sir.
Yes, sir.
It means it has some radial component of velocity.
Yes,
Hmm.
sir.
What about if you have a fluid element here, will it rotate about its own axis or not?
Yes, sir.
Have you seen it rotates or not?
Yes, sir.
Think about it carefully. This is the wash basin.
टोरॉइड सर, टोरॉइड जैसी शेप बनती है ना उसकी, जब बहुत सारा पानी इकट्ठे लास्ट में
हाँ, ये
सिंक
ऐसे आता है
होने
ना, ये
लगता है.
ऐसे जा रहा होता है.
यस सर, शायद.
तो यहां पे अगर आपका फ्लूइड एलिमेंट पड़ा है, तो क्या यह फ्लूइड एलिमेंट अपनी एक्सिस के अबाउट भी रोटेट करता है कि ये ऐसे ही मूव करता रहता है?
नहीं सर, रोटेट नहीं करता है.
ये रोटेट नहीं करता है. आप समझ रहे हैं? ये रोटेट नहीं करता है. तो इसका मतलब क्या हुआ?
ये कर्वीलिनियर पाथ फॉलो कर
देखो,
रहा है टाइप.
स्ट्रीमलाइन का कर्वीलिनियर होना और फ्लो का रोटेशनल होना एक बात नहीं है. So
Yes,
please
sir,
remember,
बिल्कुल.
when I say rotational flow, it means the fluid element has rotated about its own axis. But in this case, the fluid element is not rotating about its own axis. Although the fluid element itself is moving along a circular streamline. So now I am telling you a very interesting concept in this now, which we will be applying. There is something called vortex. Have you heard about vortex? Vortex.
यस, वो टॉर्नेडोज के बीच के पोर्शन के बारे में सुना.
So vortex means you have some kind of circulation, and that circulation is concentrated at a point. So this kind of flow that you see in a sink is actually a combination of two irrotational flows, that is a sink and a vortex. ये सबको समझ आता है कि सिंक एक irrotational region of flow है, ये तो समझ आता है, because something is converging. Had it been source also, this is irrotational. That is clear. ये तो clear है सबको. Why I am calling vortex as irrotational? Can vortex be irrotational? What do you think? If I ask you, in case of sink only, if I ask you what is the value of circulation, what is circulation? Do you remember Stokes' theorem? What is Stokes' theorem? Quickly. What is Stokes' theorem? Integral of a derivative over some region in space is equal to the value of the function at the boundaries. So this was an open surface. So open surface has the boundary of a simple loop. So this is what is there in case of Stokes' theorem. Now, if I try to evaluate the right hand side, what is right hand side? If there is some loop, you calculate the dot product of velocity vector and di vector at each and every point along the loop, you will get this integral value. Now, let me know, I am putting it here. Say I have some loop here. What will be the value of this integral along this loop? So this is the drain and this is the sink. What do you think should be the value of circulation? And this is called the circulation. This is defined as the circulation. That is the line integral of velocity vector, closed line integral of velocity vector and displacement vector. What do you think will be the value of circulation along this path? हाँ जी बताइए. What do you think? Physically, don't go into mathematics. Will there be any vorticity here? in this
नहीं
region?
sir.
हाँ जी,
फिर वो बीच वाला क्या है, सिंक है?
यहाँ पे
ब्लू,
ड्रेन है,
ओके,
ये आपका सिंक है, और
यस सर,
फ्लूइड आपका फ्लो कर रहा है वैसे ही जैसे आपका कर रहा था कि यहाँ पे ऐसे ऐसे।
यस सर,
तो मैंने एक ब्लू कर्व ड्रॉ कर दिया, क्लोज कर्व इस रीजन में। माय क्वेश्चन इज this closed integral along this loop will be zero or non-zero?
जीरो होना चाहिए सर।
Zero.
यस सर,
Here,
जीरो ही होगा, जितना आ रहा है उतना जा रहा है।
what about this? I have a loop like this, say
यहाँ पे नॉन जीरो होगा सर।
non-zero. यहाँ पे एक ही पॉइंट पे वॉटिसिटी कंसंट्रेटेड है। So please remember, all other region except this singularity point is what region? Irrotational region. Is that clear?
यस सर,
So please remember, uniform flow, a source or a sink or a vortex, all of them are irrotational elementary regions of flow. एलिमेंट्री मैं इसलिए कह रहा हूं, इनको हम कंबाइन करेंगे। जैसे हमने किनको कंबाइन किया तो हमारे पास एक्चुअल प्रैक्टिकल फ्लो पता चल गया। जब हमने सिंक और वॉटेक्स को कंबाइन किया, हम एक्चुअल फ्लो को सिमुलेट कर पाए जो एक सिंक में होता है। हाँ जी, क्लियर है? क्योंकि अकेला वॉटेक्स अगर होता तो यहां का फ्लूइड एलिमेंट अंदर तक ना पहुंच पाता, सिर्फ घूमता ही रहता।
यस सर,
तो जो आप सिंक में देखते हो, दैट इज एक्चुअली कॉम्बिनेशन ऑफ दीज टू, दैट इज अ सिंक एंड अ वॉटेक्स। सो यू कैन एक्चुअली कंबाइन two elementary flows to get a practical flow condition. यानी क्लियर है?
सर इस टर्म को कहते क्या है, ये जो स्टोक्स थ्योरम लिखी है उसका LHS RHS?
इसको बोलते हैं सर्कुलेशन। सर्कुलेशन, इसको
मतलब
रिप्रेजेंट करते
फिजिकल
हैं कैपिटल गामा सबस्क्रिप्ट सी।
सिग्निफिकेंस क्या होती है सर, मतलब
सर्कुलेशन इज बेसिकली कितनी मैग्नीट्यूड है वॉटिसिटी की।
अच्छा, ओके सर,
एक तो आप मैग्नीट्यूड ऐसे पता लगा सकते हो, ठीक है,
हाँ,
और एक ऐसे पता लगा सकते हो। both are different ways to find out the magnitude of the vorticity. Any clear है? Any doubts? Now I'm coming to another elementary flow region, and that is called a doublet. Doublet का मतलब क्या है? एक आपके पास सोर्स है और एक आपके पास सिंक है, और ये आपस में बहुत क्लोज हैं। तो फ्लूइड कैसे फ्लो होता दिखेगा आपको? कुछ ऐसे। So when this distance between, हाँ जी बताइए, क्या कह रहे हैं आयुष?
सर आपने ये क्या बनाया हुआ है लेफ्ट हैंड साइड में?
ये वाला?
हाँ सर,
ये सोर्स है। सोर्स, ये क्या सिंक है,
और ये वाला
सिंक है। ये सोर्स है, ये सिंक है, ये आपस में बहुत क्लोज हैं। तो यहां से सोर्स से फ्लूइड निकलेगा, सिंक में जाएगा, इस तरह से। So this is also called a elementary irrotational region of flow. This is also called an elementary irrotational region of flow. तो हमने अभी एक कौन कौन से डिफाइन कर दिए हैं एलिमेंट्री irrotational region of flow. One was uniform flow. Second was source. Then sink. Then
vortex.
Then a doublet. Doublet means source and sink together. This is called a doublet. Just in a moment you will get to know why we have defined this. इतना आपको समझ आ गया कि जब हम सिंक और वॉटेक्स को कंबाइन करते हैं हमारे पास क्या प्रैक्टिकल सिचुएशन क्रिएट हो जाती है जो एक वॉश बेसिन में होती है. तो वॉश बेसिन के फ्लो को सॉल्व करने के लिए आपको नेवियर-स्टोक्स इक्वेशन ना करनी पड़ी यूज. आपने सिंपल क्या किया, पोटेंशियल फ्लो थ्योरी में इन एलिमेंट्री फ्लोज के पोटेंशियल फंक्शन या स्टीम फंक्शन को ऐड कर दिया सिंपली, और आपके पास एक्चुअल में वेलोसिटी और वेलोसिटी फील्ड आ गई. क्योंकि आपको फाई और साई पता चल गया, अगर तो वो पता चल गया तो आपको यू और वी पता चल जाएंगे. सो दैट इज द यूटिलिटी ऑफ यूजिंग these elementary irrotational regions of flow. Now I'm combining another kind of flow. This is a uniform flow, and this is, say, a doublet. So if you combine these two kinds of flow, what kind of flow will you get? What kind of flow will you get? Try to think about it. What kind of streamlines will you get?
फिर वो घूम के वापस आ रही होगी.
ऐसे आ रहा होगा, कुछ ऐसा आ रहा होगा. Is this clear? और एक ऐसी भी स्ट्रीमलाइन होगी, आप देखोगे कि ऐसे गई फिर पूरा घूमा सर्कल, फिर एक ऐसे. So these two are actually simulating flow over a circular cylinder. तो अगर आप इन दो पोटेंशियल फ्लोज को कंबाइन कर दो तो जो स्ट्रीमलाइंस रिजल्टेंट बनेंगी वो स्ट्रीमलाइंस किससे मैच कर रही हैं या किसके क्लोज हैं. जो स्ट्रीमलाइन जनरेट होंगी, अगर कोई यहां पे सिलेंडर पड़ा होता और उसके ऊपर से यूनिफॉर्म फ्लो हो रहा होता तब भी तो ऐसी स्ट्रीमलाइंस बनती है, आपको याद होगा. हाँ जी, क्लियर है. So time has, wait for a second. Wait for 1 minute only. हाँ जी, ये क्लियर है. आकाश,
Yes, sir.
राजंश,
Yes sir, बिल्कुल.
ठीक है. तो we will continue with this point forward, and only one thing you need to think about when you come to the next class. What is the disadvantage of this? इस केस में क्या हो रहा है, गलत क्या आ रहा है कि आपको यहां पे भी वेलोसिटी मिल रही है फ्लूइड की, इसके सरफेस पे भी, और एक्चुअल में क्या होता है, देयर इज ऑलवेज अ नो स्लिप कंडीशन एट द बाउंड्री. तो इस एनालिसिस में सिर्फ एक ड्रॉबैक है कि इसकी स्ट्रीमलाइंस या इसकी जो यूटिलिटी है वो इस रीजन में करेक्ट नहीं है. And we will look at it in more detail. I will break for today now.
सर अब अभी तक ये एरोटेशनली है ना?
हाँ, ये सब कुछ ये रोटेशनल रीजन ऑफ फ्लो के लिए हमने बनाया हुआ।
यस सर, एयर रोटेशन ही आएगा अभी तक।
हाँ,
यस,
ठीक है, ओके देन,
थैंक यू सर।
ओके।